Welcome to the fascinating world of quantum topology. In this presentation, we will explore the intriguing intersection of knot theory, quantum field theory, and topological quantum computing. Get ready to delve into a realm where mathematics meets physics in unexpected and profound ways. Let's begin with the fundamentals of knot theory. Mathematical knots are closed curves existing in three-dimensional space, with a unique property. They cannot be untangled without cutting them. Unlike the common knots we use daily, mathematical knots have no loose ends, forming a continuous loop. The key to distinguishing different types of knots lies in what are known as topological invariants. These are properties that remain unchanged, even when the knot undergoes continuous deformations. These invariants help us classify and understand the different types of knots. Moving beyond individual knots, we encounter links. Links are collections of disjoint knots in three-dimensional space. Imagine several closed curves that may be interlinked in complex ways. These are mathematical links. To understand and differentiate these links, we use quantum invariants. These are topological properties that are computed using quantum field theory methods. These methods generate polynomials that are unique to each link type, enabling us to distinguish them. One of the most significant breakthroughs in knot theory is the discovery of Jones polynomials. Discovered by von Jones in 1984, this knot invariant revolutionized the field of topology. It established a connection between knot theory and quantum field theory. Jones polynomials are Laurent polynomials, expressed in terms of t raised to the power of 1/2. These polynomials distinguish knots by their topological structure and chirality, essentially differentiating a knot from its mirror image. Jones polynomials have several key properties. First, they can detect chirality, which means they can distinguish between a left-handed knot and a right-handed knot. This is done by substituting t with t raised to the power of -1 in the polynomial. Second, the polynomial span provides lower bounds on the minimal crossing numbers of knots. The skein relation is a fundamental recursive relation for computing Jones polynomials. The skein relation is expressed as follows: t raised to the power of 1/2 minus t raised to the power of -1/2 multiplied by v of L subscript 0 is equal to t raised to the power of -1 multiplied by v of L subscript plus minus t multiplied by v of L subscript minus. The connection between knot theory and quantum field theory was further illuminated by Edward Witten in 1988. Witten demonstrated that Jones polynomials arise naturally from three-dimensional quantum field theory. In this framework, knot invariants are computed as vacuum expectation values of Wilson loops in Chern-Simons theory. The Chern-Simons action is expressed as follows: S subscript Cs equals the integral of trace of a wedge de plus 2/3 a wedge a. This is a topological field theory that produces knot invariants. Topological quantum field theory, abbreviated as TQFT, provides a mathematical framework where physical observables depend only on topological properties and not on the metric structure. A key aspect of TQFT is its functorial structure. This structure connects manifold topology to vector spaces and linear maps between them. The TQFT functor is expressed as follows: z from cobord to vex subscript c, which maps cobordisms to complex vector spaces, preserving composition. Witten's 1988 breakthrough demonstrated that Jones polynomials emerge from three-dimensional Chern-Simons gauge theory at a quantum level. In this approach, knots are represented as Wilson loops. These Wilson loops are gauge invariant observables in quantum field theory. The Wilson loop expectation is expressed as follows: angle bracket w subscript r of k angle bracket equals v subscript r of k. This means that the vacuum expectation value of the Wilson loop equals the knot polynomial. Now let's explore topological quantum computing. This is a revolutionary paradigm that utilizes anyonic braiding. This is topologically protected from local perturbations and decoherence. Topological quantum computing offers inherent protection against errors through non-local storage of quantum information in topological states. This makes it a promising approach for building more reliable quantum computers. At the heart of topological quantum computing lies the concept of non-abelian anyons. These are exotic quasiparticles found in two-dimensional systems. Their exchange operations generate non-commuting transformations on quantum states. The world lines of anyons form braids in spacetime. These topological structures naturally encode quantum computations. This approach provides a robust way to perform quantum computations. Quantum topology and topological quantum computing have a wide range of applications. One prominent application is in quantum simulation. It helps in modeling complex quantum many-body systems and materials. It provides topological protection against errors. Another application is in cryptography. It provides post-quantum secure communication protocols, leveraging the computational complexity of knot invariants. An example of a system is the Fibonacci anyons. They follow the fusion rule: tau times tau equals 1 plus tau. These golden ratio fusion rules enable universal quantum computation. The field of quantum topology is continuously evolving, with exciting future directions. There is ongoing experimental progress in advancing anyonic systems, improving material fabrication, and creating scalable quantum architectures with enhanced topological protection. There are also continuous theoretical developments with new TQFT models, refined knot-invariant computations, and deeper connections between topology and quantum information. There are challenges that need to be addressed. These include material purity and anyon manipulation, scalability and precise braiding control, and environmental decoherence mitigation. These challenges will pave the way for advancements in the field. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.